If you place an electron near a positive charge, it snaps straight toward it. The rules of static electricity are linear and predictable, but when energy flows through a wire, the resulting magnetic field behaves entirely differently. In 1820, Hans Christian Oersted demonstrated this difference. By closing a circuit, the electric current flowing through the wire created a magnetic field strong enough to perform physical work, deflecting a nearby compass needle. The inverse phenomenon is equally strict. An external magnetic field exerts a physical force on a charged particle, but only if that particle is moving. Unlike gravity pulling an object straight down, or an electric field pulling a charge straight across, the magnetic force pushes a moving particle sideways. This sideways push is an orthogonal force. It acts perfectly perpendicular to both the particle's trajectory and the orientation of the field itself. By tracking the vector math of a single isolated electron, we can scale the geometry up to explain the massive electromechanical forces that drive industrial motors and power global grids. Consider a single positive charge moving through a vacuum. It has a specific velocity, and it enters a grid of parallel lines representing a uniform magnetic field. The parameters of this interaction are defined by the Lorentz force equation. The total force is calculated using the amount of charge, its velocity, the strength of the magnetic field, and the sign of the angle between the particle's path and the field lines. This diagram illustrates how to predict the exact direction of that force using the right-hand rule. By aligning your forefinger with the magnetic field and your middle finger with the particle's velocity, your thumb indicates the direction of the resulting magnetic force. In physics, doing mechanical work requires a force to be applied in the direction of an object's displacement. Because the magnetic force is geometrically locked at exactly 90 degrees to the particle's velocity, the cosine of the angle in the work equation is 0. This creates a strict kinematic rule. A magnetic field can never speed a particle up or slow it down. The particle's kinetic energy remains completely untouched. A magnetic field functions strictly as a steering mechanism, forcing particles to turn while maintaining a constant speed. When a particle enters the field perfectly perpendicular to the magnetic field lines, the orthogonal push acts continuously. The force vector constantly shifts to point toward a center axis, trapping the particle in a closed circular loop. By equating this magnetic force to the centripetal force required for circular motion, we arrive at the specific equation for the loop's radius. A heavier mass or a higher velocity will widen the circle. Conversely, increasing the strength of the magnetic field tightens it. In applied engineering, particles rarely enter a field perfectly straight on. They enter obliquely, at angles between 0 and 90 degrees. This diagram demonstrates how vector math splits this oblique velocity into two independent components, one parallel to the field lines and one perpendicular. The parallel component travels freely, ensuring continuous forward motion. The perpendicular component generates the circular orbit. Combining these two independent motions yields a helical spiral. Complex trajectories are simply the sum of isolated vector rules playing out simultaneously. To scale the math from a theoretical vacuum to a physical solid, the underlying physics remain identical. An individual electron is now one of billions flowing through the rigid crystalline lattice of a copper wire. A current-carrying wire is just a constrained river of moving charges. This diagram shows what occurs when we place that physical wire inside a uniform magnetic field. The magnetic field does not push on the stationary copper atoms. It interacts exclusively with the moving electrons. As billions of electrons experience the microscopic sideways Lorentz force, their paths curve and they collide with the boundary of the wire. These internal collisions transfer the aggregate microscopic forces into a single macroscopic push on the solid object itself. The math scales directly. The individual charge and velocity of an electron translate precisely to the total current and the physical length of the wire in the field. Every physical motion generated by electricity, from a vibrating loudspeaker to an industrial generator, is the result of billions of microscopic Lorentz forces pushing against a metal cage. We test this by placing two straight, current-carrying wires parallel to each other. Wire 1 acts as the generator, and wire 2 is the target. The concentric field expands from wire 1, establishing the specific field direction where it strikes wire 2. Applying the left-hand rule to wire 2 reveals that the resulting mechanical force vector points directly back toward wire 1. If you reverse the direction of the current in wire 2, the resulting mechanical force vector flips outward. Parallel currents flowing in the same direction physically attract each other, while currents flowing in opposite directions violently repel. Focus purely on standard physical dimensions, 2 infinitely long wires placed exactly 1 meter apart in a vacuum. When 1 unit of current flows through this setup, it generates an exact mechanical force of 2 × 10⁻⁷ newtons per meter. This physical setup and resulting force measurement is the literal, internationally accepted definition of 1 ampere. The foundation of all electrical measurement relies entirely on the kinematics of magnetism. The exact same orthogonal force that traps a single electron in a helical spiral is the structural rule that dictates the mechanics of our physical world and the baseline definitions of modern physics.